All right, today we're going to unlock a surprisingly powerful tool in math and physics, resolving vectors. It really is like a cheat code that lets you solve some seriously complex problems just by turning them into basic arithmetic. So let's just dive right in with a challenge. Picture a four-way tug of war. You've got four people all pulling in completely different directions. How in the world do you figure out where the object in the middle, in this case a piece of candy, is actually going to go? To get our heads around this, we're going to use a great scenario from our source material that frames the problem perfectly. A classic sibling squabble over the last piece of candy. A sticky situation for sure. Okay, so here's the setup. You've got Lonnie pulling with 8 pounds of force. Connie's pulling with 10, and Cynthia is really going for it with 12 pounds. And look at those angles. They're all yanking in these completely different directions. So the big question is, what does Terry have to do to create a perfect stalemate so the candy doesn't move an inch? Now, if you tried to solve this the old school way with pure geometry, oh man, it would be an absolute nightmare. We're talking messy triangles, the law of cosines over and over again. It's complicated, it's painful, there just has to be a better way, right? And there is. This is it. This is the cheat code. Instead of wrestling with all those crazy angles at the same time, we're going to do something much, much smarter. We're going to break every single pole, every vector, down into its most basic parts. And you can see the difference right here. The hard way? It's just a jumbled mess of triangles and angles. But the easy way, our cheat code, is just about breaking every single one of those forces into a simple sideways pole and a simple up and down pole. And once you do that, the whole thing becomes a simple addition problem. It's kind of beautiful. Okay, so to use this method, we just need a couple of simple tools. So let's build out our toolkit right now. First thing you need to know is something called component form. And don't let the name scare you, it's super simple. It's just a way of describing any vector with two numbers. How much it moves sideways, that's x, and how much it moves up or down, that's y. And you can think of these x and y movements as being made from two fundamental Lego blocks. The vector we call I is just a single step to the right, and the vector j is a single step straight up. That's it. Any vector you can imagine, like 3, 4, is just a recipe. Take 3 of those I blocks, so 3 steps right, and add 4 of the j blocks, 4 steps up. So the big question is, how do we get from the force and angle we started with to these super simple x and y parts? Well, we use these two straightforward formulas. The horizontal part, x, is just the magnitude or the strength of the pole times the cosine of the angle. And the vertical part, y, is the magnitude times the sine of the angle. Seriously, that is the whole trick. All right, our toolkit is ready. Let's go back to that messy tug of war and see just how easily our little cheat code solves the whole thing. Just look at how clean this becomes. We take each person's pull, their force, and their angle, and we just pop them into our formulas. Lonnie's pull breaks down into a sideways part and an up and down part. We do the same for Connie and the same for Cynthia. Suddenly, all that chaos is organized into these nice, neat columns. And here comes the magic. This is the best part. We just add up all the horizontal forces to get one total x component. Then we add up all the vertical forces to get one total y component. And that's it. That number represents the total combined pull of all 3 siblings. No geometry, just simple addition. So, for the candy to stay perfectly still, Terry has to pull with a force that is the exact opposite of that combined total. So if the siblings' combined vector is negative 3.44, 3.04, Terry just needs to pull with positive 3.44, negative 3.04 to cancel them out perfectly. So what does that mean in the real world? It means Terry needs to pull with about 13 pounds of force in a very specific direction to create that perfect stalemate. And just like that, we've solved it. You know, this technique is not just for fights over candy. It's exactly how you'd calculate a plane's true path when it's being pushed around by the wind. You just treat the plane's own power as one vector, the wind as another, break them down, and add them up. So why is this math trick so important? What's the really big takeaway here? Well, the power of components is that it takes messy, real-world geometry and transforms it into clean, simple arithmetic. It makes combining a bunch of different forces, whether it's people pulling or winds blowing, incredibly easy. It's a foundational tool for pretty much all of physics, engineering, and even computer graphics. But you know, This is more than just a math lesson. It's really a strategy for problem solving. So let me leave you with this. Where else in your life can breaking down a huge, complex challenge into simpler, more manageable parts lead you to a surprisingly elegant solution?